All right, welcome to AP Calculus Online Edition, or hashtag quarantine. I don't know what we're calling this. This is the lesson that we left off with before break. If you're in fourth period, you already got this lesson unless you were absent, so now you're doing it, and if you're in third period, this is new for you. So you'll need a couple things for this lesson. Item one is you'll need this notes packet that's right here on the screen. You can get this just from the assignment section of Teams. It'll say day 92 assignment area between two curves. You click into it, there's a resources section, open the attachment, cool. So you can print that off. If you don't have a printer, that's okay. You can just take notes by hand too, right? You've got this video in front of you, take notes by hand on what's important, and you'll definitely have to do the 6 problems at the end, but that's about it. The other thing you'll need is a graphing calculator. As a reminder, TI, if you search for free TI license, they're doing a 6-month free license for TI 84s and for TI Inspires that you can download onto your home computer or any computer. Not sure if it works on a phone, but definitely a computer. So if you don't have a graphing calculator, you can use that to get a graphing calculator on your computer. And that's what I'm going to be using too. So this packet, graphing calculator, willingness to learn, let's get started. The opener you can read to yourself. You should pause this video quickly and then try this part right here. I'm assuming you're going to pause it. And you've now unpaused. Wonderful. So hopefully you all found that the bounded area was 15. Okay, now how do we write an expression involving intervals or integrals that produces that answer? Well, let's do it with colors. This first integral is measuring the area from a to b underneath f of x. So here is the f of x region we care about, and here is the area between f of x and the x-axis. Looks something like that. And that is, of course, 20. And I'll box it just so we can keep track of it. That is too much. So we're going to start with a to b f of x dx. That is too much, and we can tell it's too much because it's more than the green area here. So then we're going to take our second function. I'll do this one in yellow. Our second function is g of x, and if we measure the area of g of x, that's just this little portion right here. And of course, what do we do with the whole area and the smaller one? We subtract them, and it's going to look something like this. And huzzah, we do 20 minus 5. Now realize that we could also write this as one super integral if you want, and this would be from a to b of f of x minus g of x dx. Okay. Now, couple things to note here. First, we did the top function minus the bottom function, and that gave us the area in the middle, and that's pretty much going to be the theme of today, top minus bottom. Now, what we're really doing though, and this will become important later on, is we have to realize that when we do an integral is summing up this multiplication problem on the inside. And remember, if we're just working with f of x times dx here, then what we're doing is we're building a rectangle that has a height of f of x, and I'll build this rectangle right here. Well, that's just a line. We need to give it a width though, and the width is infinitely small, and we call that dx. Okay, and then this builds one rectangle. We do the math, that finds us the area of one rectangle, but then we have to do lots of them, and then of course sum them up, which is why the integral is just a large S. Okay, now a couple things to notice here. This dx, this width, is along the x-axis, and everything in this integral has to do with the x-axis, f of x dx, and these are both x values. Okay. Now what we're really doing is we're taking a big rectangle and then we're taking a small rectangle on the inside, we're subtracting the two of them together, and we get this inner rectangle. So as a follow-up question, by the way, could the area between the two curves ever be negative? Well, I think as long as you stick with top minus bottom, you'll be just fine. So if you think of top and bottom as y values, maybe we'll take this y value right here is 7, and we'll pretend this y value right here is like 2. If I do 7 minus 2, that is certainly a positive answer. But then what if the graph shifted? What if my x and y axis was something like this? And now let's pretend this top value is like 3 and this bottom value is like negative 3. Still positive? Well, we do top minus the bottom. Oh, 3 plus 3, that is still positive. But then the big one. what if our x-axis shifts again? And now instead of it being in the middle, let's make everything negative, and let's put the x-axis way up here. Okay, here's my x, here's my y, and now we have a y value of something like -2 and a y value of something like -5. And if I do the top minus the bottom, is it still positive? Oh yeah, -2 plus 5, that is still positive. So yes, right? Would the area between two curves ever be negative? Or I guess I should probably say no here. The area will always be positive. Now, the nice part about this is the order doesn't really matter, because if you do top minus bottom, or what you think is the top and what you think is the bottom, and you get a negative answer, then probably you just switch the order. Try switching the integrals, and you're going to get the same answer, just negative versus positive, right? If I looked at this last one, -2 plus 5 is 3. If you'd switch the order, -5 minus -2, you get -3. It's the same answer, just the sign is switched. So keep that in mind. Here we go. In summary, we find the area between two curves by doing the integral of the top curve minus the integral of the bottom. So I have a quick example here, and I'd like you guys again to pause my wonderfully soothing voice and see if you can figure out this example. Now, it says, which of the following expressions gives the area enclosed? And as a hint, there might be more than one right answer. In fact, there is more than one right answer. So go ahead and pause me, think about it, and once you think you have the answer or answers, unpause me and I'll take you through it. Alright, you've unpaused me, I got a chance to take a breath. Let's go through these one at a time. So here are the areas that we are interested in, and we should also probably label these functions. We have y equals x that I'm going to do in purple, and that is this beautiful, uh-oh, that was terrible. We have this beautiful 45-degree angle line, and it looks like this. Then we have our wonderful second function, which is just g, and g I'll do in yellow. Something like that, give or take. Okay, and the question is, which integrals below 1 through 3 will give us the actual area between the two curves? Now there are two areas here. Okay, so and I'm just going to make up a couple y values here. So let's just call this y value 1, and we'll call this y value underneath, oh, let's just make it easy, let's call it 0.5, right? Nothing bad. And then we can do the other one. Let's call maybe this y value 1.5, and being wrong, but let's also call this one 1. I know it's not. Okay, now think about if we do the yellow function minus the purple function. If I do g of x minus the purple function, which is f of x, all the way through. So I take this little region, top minus bottom, 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 all the way through g minus f. Now, hopefully you're already seeing that there's going to be some issues here. Okay, well, if you do the yellow function minus the purple, 1 minus 0.5, that's positive 0.5, that's good. The yellow function is on top all the way through here, so we do want to do top minus bottom. But if I continue to do yellow minus purple, and I do yellow minus purple here, that's going to give me 1 minus 1.5, that's going to give me a negative answer, because we're doing yellow minus purple, and that's a no-go. So if you think logically about what has to happen, we need to do yellow minus purple up until this point, and then what do we need to do? Oh yeah, purple minus yellow. Now that's exactly what you're going to see on answer number 3. Answer number 3 here is going to do yellow minus purple until we get to an x value of 1. Notice these are always x values, right? An x value of 1, and then after an x value of 1, it's going to do purple minus yellow, which is excellent. This will give us the right area in between the two curves. But what about the other two? Well, the second one is an interesting one. The second one says do x minus g of x. So it's saying do the purple minus the yellow. Well, purple minus yellow is going to be great here. So that one is good to go. Just put a little check in here. However, the issue of doing purple minus yellow here is going to be bottom minus top. You're going to get negative area. But what's happening to that area every time? Well, it's saying after you find the area, so the first thing it's going to do is find the area of x minus g of x. And then the second thing it's going to do is, of course, these absolute value bars. So it's going to take the area, whatever the area is, it's going to make the area positive, And then last but not least, it's going to sum, all right, sum up all the area. And I think that would be okay, because if I did 1 minus 0.5, that'd be positive 0.5. That's what I want. This, though, is telling us to go backwards. 0.5 minus 1 is negative 0.5, but then the absolute value turns it back into positive 0.5, and we're in business again. So 2 is actually okay as well. Well, what about 1? 1 looks exactly the same as 2, doesn't it? I mean, slight difference. They move the absolute value on the outside, but does that matter? Well, I think it actually does here, because what they're going to do here is first they're going to find the area doing x minus g of x, and then second they're going to sum up all the areas. So that means they're going to find some negative areas here, some positive areas here, and then sum those two up. Well, those areas look the same to me. If you add a negative and a positive up, that's going to give you 0. And then it's going to apply absolute value at the very, very end. Oh, so I think by order of operations, this one is a no-go. So 1 doesn't work, 2 and 3 do. All right, so here we go. That is our basics for today, right? Top minus bottom. So now we're going to branch off a bit and see how we do with functions. So you're going to pause me again, and your goal is to graph both of these equations, preferably without a calculator, and see what you come up with. Okay, pause me, ready, set, go. And you've unpaused. Hopefully you had these functions done quickly, right? Down 3, and then, I mean, it's a parabola. It's not going to be perfect, right? It's just going to look, it's going to be a little wider than normal, so something like that. Okay. And then this one is a little bit more interesting. Now, you could make a table to get your answer, but this is in terms of x equals. So let's apply exactly what I did on the left, but to the right. This one dropped us down 3 on the y-axis. So this equation will drop us down, air quotes, 3 on the x-axis. And then once we were down, it opened us towards the positive side of the y-axis. So this is going to open towards the positive side of the x-axis. Right? By switching x and y, does anyone remember what these are called? These are inverse functions of each other. However, it's kind of weird to see x equals something, but sometimes we see it. In fact, if you solve for y, you'd have to get a square root and then a plus minus. You'd actually need 2 equations instead of just this nice 1 equation. So, how does this help us? Well, here we go. Our goal is to figure out the area between these two graphs, orange and purple. Okay, so the first thing, without even sketching a graph, let's figure out where these two intersect. Well, we have 2 equations. If we want to find where they intersect, a lot of people say, oh, set them equal to each other. But that's not really a math thing, set them equal to each other. It's more a system of equations, right? And with a system of equations, if we know that x is equal to something, then that means in my second equation I can replace x with what that equals. So I'm going to start with the purple equation, which is y equals something, right, minus 1. But instead of the something, we're going to replace that with my orange equation, 1/2 y squared minus 3. Okay, so we get y equals x minus 1. And then simplifying some things down. So let's see, as we simplify, I'm getting y equals 1/2 y squared minus 4. I don't like that fraction, so I'm going to multiply everything by 2. 2y equals y squared minus 8. Y squared's positive on the right side, so let's subtract the 2y. Get y squared minus 2y minus 8. Oh, this looks like factoring to me. So we end up with something like this. Y minus, it's got to be minus 4, positive 2, which gives us y equals 2 answers, negative 2 and positive 4. But if we want to find where they intersect, those are just the y values. We also, of course, need our coordinates. So we'll do them down here. There's going to be 2 coordinates here. We know the y coordinate of the first one's negative 2, the second one's positive 4. How can we find the x's? Oh, well, there's some nice equations over here. In fact, let's even manipulate this one a bit. Let's add 1. We take the y value, add 1, and it gives us the x. Alright, so let's take the y value 4, add 1, and that gives us an x of 5. Take the y value negative 2, add 1, that gives us an x of negative 2. Ha! We found where they intersect. Decent amount of work there, but we're doing okay. Alright, Well then, let's actually sketch a graph of what we're trying to do, because we want to find the area between or enclosed with these two graphs. So here we go. We're going to probably have to redraw this once or twice, but that's okay. We already know what this graph looks like actually, so let's be a little more careful. 1/2 y squared minus 3. We only need to go down 3 on the x-axis. Okay, but I don't quite know. Let's see. On the y-axis, we have to go up to at least 4. So let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Definitely have to go down 3 here, and then we'll just go a ways over. This might be wasted space, but that's okay. All right, x equals 1/2 y squared minus 3. We already said it looked something like this, and we know two other points on here. We know the point -1, -2. Of course, by symmetry, -1, +2. And then we also know the point 1, 2, 3, 4, 5, comma 1, 2, 3, 4. And by symmetry, 5, comma 1, 2, 3, -4. Look at that nice parabola. And I said I'd do this parabola in orange, it looks like, so let's get it done. Ah! Missed it. That's okay. There we go. There's one. And there's the second one. Cool. And then the second graph we need is y equals x minus 1. Well, that's just a diagonal line, nothing too bad. We'll do it in purple. It starts down 1 right here. And we already know all the other points on here, right? We can put the rest on here and see how poorly I did with making a straight line. That's awkward. Oh, that's because I missed that, though. So here we go. Second try. Ah, that's much better. Okay. And we get our beautiful purple line. All right, now can we see the area here? I'm going to erase this in a second, but this is the area enclosed between the two graphs. We're trying to figure out how much area is that. Well, let's just do what we've done on the first page. We just did top function minus bottom function, right? So it seems to me like the function that's on top is the one that I did in orange, and the one that's on the bottom is purple, right? Orange minus purple, orange minus purple, orange minus purple. Uh-oh. Look at the end. After we cross that second intersection point right here, when we do top minus bottom, now you have a function minus itself, and that's a no-go. So you have a couple options here. The first is, why do we get a function minus itself? Well, that's because this function up here is really two different equations. If you solve for y, you're going to get a positive square root and a negative square root. And then when you do a positive minus a negative, you'll get an answer. But I don't want to have to change that around. So instead, let's just go through, and instead of doing top minus bottom, notice that top minus bottom worked because we were doing a big y value minus a small y value. But we can't be, biased towards different values. If we can do that with y values, can't we do that with x values too? What if we were to take a big x value like 1 and subtract a small x value like -3. Right minus left, 1 minus -3. Oh, well, that's not too bad. 1 minus -3 gives us an area of 4. So can we just do right minus left? Let's see. If I do the right function, and I think every single time you have points here, and I'm just drawing a couple corresponding points, I think my right function will be the purple one, and the left function will be the orange one. So I'm doing right minus left instead of top minus bottom, which basically means we're subtracting the x values. So the issue with trying to find the area is we can't do top minus bottom consistently all the way through. We have to change functions, things get weird. So top minus bottom, and I'm just going to put a sad face. Okay. However, we are going to go ahead and do right minus left, which is going to be x values, and that is going to give us a happy face. So let's set up how we actually find the area. Well, we have an integral, okay, and then what do we need here? Well, the right function is, and you might want to write lightly here or just wait for a second, and I should probably keep my colors going. My right function is in purple, and we already said that was y equals x minus 1, so x minus 1. And then my left function is this 1/2 y squared minus 3, and then we usually end with like a dx or something. But now we have something not good going on, and that's that we have two different variables here. But let's just use some deductive reasoning here. When we did top minus bottom, everything in our integral was in terms of x. These were on the x-axis, a to b. these were in terms of x all the way through, and that led us to top minus bottom, subtract the y's. So if I'm going to do right minus left, what do you think my integral has to be in terms of? And hopefully you said, oh wait, y, that makes sense. We need all these to be in terms of y. Well, that means that my orange function is good to go. That has y's. But my purple one, not so much. I don't want it to be y equals. I want everything to be x equals. And cleverly, we already did that. X is actually equal to y plus 1. So it's an easy erasure here. Okay, well, then let's think about the second thing. What we're doing then is this y plus 1 and this 1/2 y squared minus 3 are creating x values. This creates an x value, creates an x, and then we subtract them. So again, using an example over here, I'm going to go ahead and draw this nice rectangle right here. Well, that's a terrible rectangle, but that's fine. We get the idea. We are subtracting x values to get the base, but then how wide is the height of the rectangle? Well, the height is along the y-axis, and in the past we've said the height is, or the height or width is infinitely small, so it shouldn't shock you that our base here is going to be dy instead of dx. Okay, so then do we just go from our x values here? Remember our x values earlier were -1 and 5. Well, hopefully you're saying no, because everything else in this problem is in terms of y. So I don't want the x values here. In fact, I want to use limits that are y values. And it's one of those where I could totally understand getting confused here about, wait, how do I know when it's x's or y's? Well, if you have one function that has a y in here, every single value needs to be in terms of y. We see a y here, so we need a y. These need to be y values all the way through. If you have something with x's, then it's going to be x values all the way through. Now, how do you find the area? We didn't actually find the area. We just set up an integral. We'll simplify it a little bit, but I'm not going to go too far. So -2 to 4, I'm going to distribute the negative and combine some like terms. So I'm getting -1/2 y squared. All right, and then I have this positive y that was hanging out over here, and then I have 1 plus 3, which is going to give us 4. Cleaned it up a little bit, but we're still not done, right? We, if we wanted to go further, would have to actually do the antiderivative, right? That's our fundamental theorem of calculus. It says do the antiderivative first. So it's going to become y cubed. 3 times 2 is going to give us -1/6 plus 1/2 y squared plus 4y, and we're evaluating from -2 to 4. Now, I'm not going to evaluate, mostly because I've run out of room and the numbers seem terrible, but you get the idea. We could go further. So, in summary, if you have one function, if one function's awkward, remains on top of the other throughout the entire region, then we integrate top minus bottom. So this is where we use functions, that already says it, functions that have x in it. However, if you have one function to the right of the other, it might be easier to integrate left minus right. That's not correct at all. That's awkward too. This should be right minus left. Oops, better every year. So once we're doing that, then we just do the same thing that we did up above, and I'll just draw a little arrow so you don't forget. Now, you guys have the rest of air quote class end quote to do the 6 problems on this back page, and for some reason the 6 problems have jumped to day 93 instead of 92. I think it's 92 though, so we're going to go with 92. There are 6 problems here. You'll notice problems 1 through 3 are no calculator, problems 4 through 6 are calculator active, and I'm going to go ahead and post this as a second video just so it doesn't run on forever, and that video link will also be posted in the assignments if you need it. So thank you for listening and getting those examples done. Go ahead and try these 6 problems that are right here, and then once you've tried them, you can go ahead and check my solutions via YouTube. Thanks for listening.